Hello students, this is the seventh lecture on the topic sequence and series. In this lecture also we will discuss some few tests of how to determine the series is convergent or divergent. So let's start. So here is another important test for checking the convergence and divergence of a series. So this is limit comparison test. Suppose that we have two series an and bn, and an is also greater than 0 and bn's are also greater than 0 for all n greater than n, that is after a specified integer n this inequality holds. Then and if you take the ratio of an and bn and take the limit n tending to infinity, you get a finite value that is greater than 0, then both the series will either converge or diverge. So you should take any series for which you know the nature, like you want to check the convergence or divergence of a series an. So you take a series bn whose nature you know, and then you divide it by an, and taking limit n tending to infinity, if you get a value, finite value c, which is greater than 0, then if this bn is convergent, then an is also convergent, and if bn is divergent, an is also divergent. Now the second is that if you take the ratio of an and bn and it comes out to be 0, then an converges if bn converges. Like if it is 0 and bn is divergent, you cannot say anything. So it is that if the limit is coming to be 0 and bn is convergent, then only an is convergent. And the third one is that if you take out the ratio and then you see that it is infinite, the limit n tending to infinity is infinite, then if bn diverges, then only an diverges. Suppose that you get infinity and bn is convergent, then you cannot say anything by this test, because if this is infinite and when bn is divergent, then only you can say that an diverges. So let us take some examples. So example number one. So determine whether the following series is convergent or divergent. So I have this series and I want to see that whether this is convergent or divergent. So I let bn is equal to 1 to infinity as this. Now in using the limit comparison test, you need to use an hit and trial method, but sometimes you can look at the series, which I call it as from 1 to infinity an. By looking at this series, you can choose some of the bn's, the possible candidates of bn, and then divide an by bn to see what is the limit of the ratios. So if I choose this bn, which is equal to summation from 1 to infinity 1 by 3n, we already know that this is convergent geometric series, because r is equal to 1 by 3, which is less than 1. So this is a convergent geometric series. So if we choose this bn and we take the limit, which will be equal to now this will be equal to a limit n tending to infinity 1 minus. Now we need to apply the L'Hopital rule to find its limit. So this will be limit n tending to infinity minus limit of n tending to infinity n 3 by n. Now we will apply L'Hopital rule over here. So this is clearly 1, and if we apply the L'Hopital rule, I'll get. So ultimately this will go towards 0 when I again apply limit n tending to infinity. So my limit for this will be equal to 1, which is finite and positive, positive and finite. So what can you say by using the limit comparison test, that whatever will be the nature of Bn will be the nature of An. So we already know that we have chosen this Bn, which is convergent G series. So by limit comparison test, our An will also converge. Therefore I write, by limit comparison test, summation of An also converges. Now let us take the second example, example 2, that I want to check out the convergence or divergence of this series. So now again, if you want to apply the limit comparison test, you need to choose a suitable Bn. So suppose that we choose a Bn, choose Bn as this, and you know that this is divergent. By integral test you have already seen that this is divergent. Now if I put limit n tending to infinity an bn, so this comes out to be, this is equal to 3 by 2, which is again greater than 0 and finite. So what can I say, that whatever will be the nature of this will be the nature of summation of an. So since I know that, since summation of n is by integral test or p series test, therefore summation of an is also divergent. Now let us consider the third example, example 3. So I want to check the convergence or divergence of this series. Now obviously, looking firstly at this series, you must be thinking that how to choose this Bn. Now let us consider that the possible choices of Bn be summation 1 by n square, summation 1 by n cube, summation 1 by n to the power 4, and so on. Now if you see that this, after this choices, if you divide it by an by bn, you will get infinity. So by direct observation, you will see that limit n tending to infinity an by bn will be infinite for summation n cube, summation 1 by, and so on. So we will not take this, because if we divide it by bn and it is coming to be infinity, then we can only say about this an when bn is divergent. However, you already know that these series are convergent P series. Now if you divide it with Bn, you are getting this limit. So from limit comparison test, we could not say anything about this An, that is our this. So we have to see, now look for these two series, that what happens if we divide An with these two series. Now if I divide it with this one, let Bn be 1 by n. Now if you find out the limit n tending to infinity An by Bn, this comes out to be limit n tending to infinity ln n square divided by n square equal to 0. Now this is divergent, and you have already seen that limit comparison, when you get the value as 0 and if Bn is convergent, then only you can say that An is convergent. However, here for this choice of Bn, here Bn is divergent. So again we cannot say anything by a limit comparison test. Now we will see what happens if we choose our Bn as summation of 1 by n square. Bn is 1 by n square. So what we will get, we will this is obviously convergent by convergent P series, you already know. So if I find out the limit n tending to infinity An by Bn, what will I get? I am getting this as 0. Now this result is valid for applying the limit comparison test. Like if we get the value of the limit as 0 and Bn is convergent, then An is also convergent. So this is working for this choice of Bn. It's working, the limit comparison test is working. So we can say that therefore summation of An also converges by limit comparison test. So you have seen in this example that you need to be lucky to find this Bn, that with which what we Bn we should divide, so that we get a valid result for to apply the limit comparison test. Otherwise you cannot say anything about the nature of An. So so hope you understand that how important is this to choose a suitable Bn. Otherwise you have to look for other test. Now sometimes the direct comparison test makes things more easier. I'll show you how. Like in the previous example only, I have this. Now we want to determine whether it was convergent and divergent. Finally, by dividing it by 1 by n square, we found that this is convergent. But after so many hit and trial of Bn, we found that this is convergent. Now we want to apply this direct comparison theorem to find the nature of this series. So what we can do is that by using some of the result, that we know that ln of n is less than n to the power c, where c is a positive constant. It is known that this inequality will always hold. So I want to make this somehow, so I'll square it first. So this will be less than, and then I'll divide it by n cube. So which is equal to this. So now we can write that n cube is less than this. This is my equation number 2. So from this equation, what we get, that this, if this one is convergent and this one is convergent, if this value will be greater than 1, then we know by the P series test that this will be convergent. So by direct comparison theorem, this will be also convergent. So I'll write summation of n will be convergent when 3 minus 2c is greater than 1. This implies that c is less than 1. So now if you take c is half, because this is less than 1. So what you will get? You will get the inequality, this. So since summation of n square is convergent, therefore by direct comparison test, this is also so by this you have seen that you can test the convergence or the divergence of any series through different tests. It is not mandatory that we will get the result by only following one test. This depends upon the user, that what he wants to apply. Sometimes limit comparison test seems to be more convenient, and sometimes direct comparison test seems to be more convenient. So it entirely depends upon the user what he wants to use. So the another test for checking whether the series is convergent or divergent is the ratio test. It says that if a and b the series of positive terms, and suppose that limit n tending to infinity, the ratio between the n plus 1th term divided by a n term is coming to be some constant k, then if this value of k is less than 1, then the series is convergent. If the value of k is greater than 1 or is equal to like if it is infinity, then series is divergent, and if k is equal to 1, then the test is inconclusive. That means that you need some other test. Now you can note that this test is mainly preferred when an contains factorial of n, and it can also be used when an has some like nth power, like when an is raised to some nth power. So then this test is useful. So now we will see few examples for solving whether the series is convergent or divergent using the ratio test. Example 1. You have this series and you want to check whether this series is convergent or divergent. So I'll write an is equal to, I can see that the nth term is this, and if I find a n plus 1, this will be n plus 1 factorial divided by n plus 1, n plus 1. Now I'll take the ratio, that is a n plus 1 divided by a n. So I'll get this is equal to the limit n tending to infinity a n plus 1 upon a n is equal to limit n tending to infinity this. Then you can see that this is equal to this I'm writing after some computation, that this will be equal to n divided by n plus 1 whole to the power n, which is equal to, so now you can see that its limit is less than 1. So by ratio test, therefore by ratio test, what we can conclude, that this summation n 1 to infinity n factorial by is convergent. Now let's see some other example also. Example 2. So you have a series and again you want to check whether this series, I'll write it as an, that this series is convergent or divergent. So I'll use the ratio test. So you need to find out the limit. So I'll just write directly, this will be which is equal to infinity, and this you can see that lies in the case 2, that this is k, the value of k is greater than 1 or infinite. Therefore by ratio test, summation of an diverges. Now we will see the last example for the ratio test. So if I ask you that what will be the nature of this, so if you find out the limit, you will see that this is coming to be 1. Which is equal to, so therefore in this case the ratio test fail and we need to apply some other test of convergence. So therefore ratio test fails since k is equal to 1. Now by some observation we can see that if you calculate a1, we see that this is which is equal to 2. This implies that a1 is equal to 2, and also you have already find out an plus 1 by an, this is 2n plus 2, and now this gives you an plus 1 is greater than an for every n greater than or equal to 1. Now since a1 is starting from 2, and you can see that this is increasing. This implies that the sequence an is increasing. Now if this sequence is increasing, like if I say 1 and 2, so now from 1 and 2 what you can conclude that limit n tending to infinity an will not go to 0, and therefore by you will apply the nth term test for divergence. This the series will diverge. I can say the series n is equal to 1 to infinity an will also diverge. It is clear that in this the ratio test fails because your k value is coming to be 1, but you applied other test, that is the nth term test for divergence, to conclude that this series is ultimately divergent. Now there is another test which is called as a root test for checking the convergence and divergence of the series. It is like if summation of an with a series of non-negative terms, and let the limit of this, you find out the nth root of the nth term, and it is coming to be k, and if the value of k is less than 1 then the series is convergent. If the value of k is greater than 1 or infinite then the series is divergent, and if it is equal to 1 again the test is inconclusive, that is you need some other test. So now this test is preferable when the series contains the term which is raised to the power n. So you can write that when terms of the series contain expression raised to nth power, the test is preferable. So now let's do some example to use this root test and show that the series is convergent or divergent. Example 1. So suppose that you have this I'll write it as in the form of an. So you have this series and you want to test whether this series is convergent or divergent. So I'll apply the root test. I'll find the nth root of this. So now if you find the limit of this, you will get 0. Now you can see from the first case this is 0 which is less than 1. So therefore summation n is convergent by root test. Now let us do another example using this root test. So suppose that you have this series and you again want to check out whether this series is convergent or divergent. So just find out the nth root of the nth term. So I'll write it as this which is equal to I'm just writing n factorial as n minus 1 n minus 2 factorial and n square as n into n. Now you can see that I can merge up this the first term and I can write this as, now clearly this limit will go to infinity and therefore summation n from 1 to infinity is divergent by root test. I hope this is clear about the root test. For more problems, go to the book Calculus and Analytic Geometry by Thomas and Finney, 9th edition, and see section 8.6 and solve the exercise 8.6. Thank you.